Welcome to this video, which is on the subject of identifying redox reactions. Our big question is, how can I tell if a redox process is occurring? There are essentially four ways to do it, and if any one of these four criteria is met, then it's a redox reaction. Reduction and oxidation always come together in reactions, so once you've identified one of them, you've got the other must definitely be happening as well. So let's start by just looking at this very simple example of a redox reaction, which is magnesium reacting with oxygen to form magnesium oxide. And probably the first time you ever got introduced to reactions like this as being oxidation reactions, you could see that because magnesium starts by itself here, and by the end it has gained oxygen. So oxidation, you said, was gain of oxygen. Now, if you were introduced to reduction at the same time, you might have been told that reduction is basically the opposite of oxidation, which in this case would be the loss of oxygen. Now, you might have wondered why that is the case, that reduction and oxidation have to come together, and probably the next thing you were introduced to is the definition of reduction and oxidation in terms of electrons, where reduction is gain of electrons and oxidation is loss of electrons. And at that point it becomes clear why one must always happen with the other, which is that if some species is gaining electrons, then there's got to be some other species which is losing the electrons in order to supply them to the first species. So in this case, you can see that magnesium starts off with a charge of 0, it ends up with a charge of 2 plus, and so it must have lost 2 electrons, whereas oxygen, in this case, starts off with a charge of 0, it ends up with a charge of 2 minus, and so each oxygen atom must have gained 2 electrons. And so we see that the magnesium, which we gained the oxygen, is also the element which has lost its electrons, and hence it's been oxidized. And this scheme allows us to see more easily that it must be the oxygen O2 which has been reduced because it has gained electrons. And there's a very, very helpful mnemonic for working these things out, which is oil rig. Oxidation is loss of electrons, and reduction is gain of electrons. Oil rig. Now, when you looked into this in a bit more detail, you might find that it's actually quite difficult to use this definition. Oxidation is loss of electrons, reduction is gain of electrons, because in many situations it's actually really hard to tell whether something has actually lost or gained electrons, especially when we've got reactions which have many species which are not actually charged. And so a more general way of looking at things is to actually look in terms of the oxidation numbers. And you're going to have to refer back to previous videos for this. But if we assign oxidation numbers here, we find that magnesium has 0 oxidation number as an element. It then increases to +2, whereas oxygen starts off as 0 like any element and then ends up as -2. And so you can see here that oxygen has decreased in oxidation number. Now, we said before that oxygen had gained electrons, so reduction must be a decrease in oxidation number. And conversely, magnesium here, which has increased in oxidation number from 0 to +2, we said it had been oxidized before, so oxidation must be an increase in oxidation number. And so we've got another way of defining reduction and oxidation in terms of oxidation number. So there's a summary of what we've got to so far. Now, there is one other way that we can use in order to decide whether we've got an oxidation or reduction process, and that we can illustrate using this reaction here, which is the hydrogenation of a butene molecule to become butane. So if we go ahead and assign oxidation numbers here, then what we're going to find is, if we start off by looking at the hydrogen here must be 0. Sorry, I use a different colour. The hydrogen here must be 0 because it's an element. Now, in the compound, we assign hydrogen to first have an oxidation number of +1, and often I would just write 10 plus 1s here, but I'm just going to write plus 1 times 10 just for brevity. Over on the left hand side, hydrogen, there were 8 of them, and they would all have been plus 1 times 8, sorry. And if that is the case for the hydrogen, the average oxidation number of the carbons, there's 4 of them, must be minus 2. Again, 4 lots of that. And in this case, it must be minus 2.5. 4 lots of minus 2.5. And so we can see from the oxidation numbers, the element that's decreased in oxidation number is actually the carbon, and the element which has increased in oxidation number is actually the hydrogen. It's gone from 0 to plus 1. And so we have another way that we can tell what has been oxidized and reduced. We can see here the carbon which has been reduced has gained hydrogen, whereas oxidation, the opposite, must be the loss of hydrogen. And so we've got our 4 different ways to tell whether something is a redox reaction. I'll summarize them here. Loss and gain of oxygen, gain and loss of electrons, decrease and increase in oxidation number, and gain and loss of hydrogen. And as I said earlier, any one of these 4 being identified, or even one of the pair in each of these 4 being identified, is sufficient to prove that a reaction is a redox reaction. And I also mentioned earlier that the gain and loss of electrons is often difficult to spot, but in fact the oxidation numbers is the sort of easier to use twin of these 2. So these guys here are really linked together very closely, but this is easier to spot. And the link here is that an electron has an oxidation number of -1. That's the link. So if an electron is gained, then there must be a decrease in the oxidation number of a species, because you've gained something which has a negative oxidation number. And therefore, these 2 are very, very tightly connected. We can also see, using oxidation numbers, why the others must be the way they are. So oxidation is gain of oxygen. Now oxygen, when it's gained, ends up with a -2 oxidation number. So if you're gaining again something negative, you must have increased your oxidation number in order to compensate for that. And therefore, oxidation will result in an increase in oxidation number. Now conversely, if you gain hydrogen, hydrogen has an oxidation number of +1. And therefore anything that's bonded to hydrogen will have to decrease its oxidation number, and therefore reduction is a decrease in oxidation number. So that's how the guys link together, and it's particularly the oxidation numbers approach that tends to get used in inorganic chemistry, whereas in organic chemistry we really tend to see a lot the use of these 2 methods. So this is very, very common in organic chemistry. And the reason is that, as we saw in the previous example with butene and butane, oxidation numbers are actually quite meaningless within the context, or average oxidation numbers at least, in the context of organic molecules. And if you have bigger molecules than these, you're going to get very, very strange numbers appearing. And in fact, what's really going on here is that the different carbon atoms in the molecule have different oxidation numbers, and that's giving you this strange fractional oxidation number here. And in fact, with organic reactions where you've got big molecules with only small bits of them changing, it's much, much easier to spot using the molecular formula that hydrogen has been lost, or in this case gained, and therefore these are the 2 methods that are most commonly used in organic chemistry, with the oxidation number method being more commonly used in inorganic chemistry. And that's how you identify redox reactions.